All right, welcome back. This is Dr. Matthew J. Trom from Engineer Inc. This is the fifth and final video in the series describing how to use the ANSYS finite element software package to simulate, model, represent the elongation of PASCO metallic stress strain apparatus sample coupon, represented here just by a metallic rectangular simulated shape. So I've got my geometry set, I've got my mesh established, I've got my 100 newtons of force imposed on one face, I've got my fixed support boundary condition imposed on the other face. I am almost ready to go. There are two things that I want to point out. One is just for your knowledge, and the other one is actually critical to getting the right answer. So you've noticed over the course of these videos that I've used the pan and the rotate functions to expose various faces and surfaces of interest that I couldn't otherwise see had I not rotated the object. But if I get myself into a situation where I just can't get back to a nice isometric view, I can always use this coordinate system, which is down here on the right-hand side of the view screen, to get myself back to a geometry that makes sense. So I can expose individual faces by clicking on Z, Y, and X. Those give me now a front-on view of that particular surface of my sample. And to get back to a nice isometric view, I can just click on this little blue ball here, and it actually says ISO to remind me if I hover over it that's an isometric view. So if I click here, bing, I'm back to my nice clean isometric view, and I can go from there. So that's how to get yourself back into an isometric view in case you get yourself off in some weird direction as a result of all of the rotating and panning. Okay, so that's one thing I wanted to mention. The other thing is, recall that ANSYS uses structural steel as its default material. And remember, in the very first video, we selected an alloy of aluminum as an alternative possibility. We added it to the library. And so at the moment, if I look at what ANSYS thinks this sample coupon is made out of, it's going to tell me structural steel. So I need to change that. So if I hover here over geometry and go to system/solid and then look down here, if I scroll down, notice right here it says assignment, material assignment, and it says structural steel. So that's bad. Steel has a much higher Young's modulus than does aluminum, and so the end result is going to be an answer very different than the one that I expect from my hand calculation, unless I get the material right so that the Young's modulus is correct. So I am just going to click on this guy, and I'm going to change it from so I could just add a new material, but remember I added that aluminum alloy to the library, so here it is down here. Had I not done that, I could have gone back and added it later, but I preemptively added it in the beginning of this series of videos so that it would be here at this point for me to move forward. So I'm going to click on aluminum alloy, and now the material assignment is in fact aluminum alloy, and I should be ready to move forward. Okay, so now I've got everything set. I am interested in a solution that gives me the deformation or the elongation of this sample. So I'm going to right click on solution, and here under insert there is a whole bunch of different possible solution types that I can go for. There's deformations, there's strains, there's stresses. I am just going to click on deformation total, which is going to tell me how much it deforms. So that's going to appear here in the project tree as one of the possible solutions that ANSYS solves for me. And we'll just add another one just for fun. So I'm going to add, how about equivalent stress? Okay, so I'm just going to add 2 just so you can see the difference when I actually do the solution. Okay, so should be ready to go. I've got my geometry set, I've got my coordinate system, I've got my mesh established, I've got my forces, both 100 Newton force here on this face and fixed support here on this face. I've told ANSYS that I am material aluminum, not structural steel, and I've told it the types of solutions that I'm looking for. I should now be ready to solve. So I'm going to hover over solution. I'm going to right click. I'm going to hit solve. And again, your computer is probably faster than mine because mine is a very low powered laptop. But that's it. Bing. Okay. So now we've got our solutions. So I'm going to first look at total deformation. There it is. Okay. So what we can see here is a color code that's just sort of set up automatically by ANSYS. The blue colors represent a relatively low deformation, and the red colors represent the more red colors represent ever increasing deformation. So remember, this end was the one that was fixed, and so the deformation there starts out at 0. Let me see if I can move. There we go. Okay. The deformation here starts out at 0, which is the minimum value. And then the deformation increases as I move down the sample to this end, which is the one where that 100 Newton force is imposed. And the value here is 3.12 times 10 to the minus fifth. Now, how does that compare to the hand calculation, right? That's an important thing that we want to check to make sure that our simulation is giving us an answer that is consistent with the underlying mechanical engineering theory. So you may not remember from the initial video, but the number there that I'm looking for is 3.13 times 10 to the minus fifth. So it is, in fact, 3.126 or 3.13 times 10 to the minus fifth. If you don't believe me, here's that original calculation, and here's the value, right? 3.13 times 10 to the minus fifth meters. So yeah, that actually agrees with my hand calculation, which is excellent. Okay, so that is an awesome result. That means that ANSYS is doing what we expect to do. It gives us the right answer. The other thing that I wanted to look at was just the equivalent stress. That was the other solution that I arbitrarily selected. So let me click on this guy, and that's what it looks like. It's essentially uniform almost all the way through, except there's a little discontinuity here at the end, and that's exactly what you would expect, right? If you impose a force on one face and the cross-sectional area is the same throughout the object, the equivalent stress should be identical all the way across, of course, until you hit this boundary condition here at the end. So that's a lot less spectacular than that solution, but it's still consistent with what we understand from the mechanics of materials class to be the correct answer. Okay. So there is one more step here. You might feel inclined to stop, knowing that we've set up the geometry, meshed the system, solved the problem, and the answer agrees with the hand calculation. But there is one final thing that you want to do when you run a finite element simulation, and that is to reduce the mesh size and rerun the simulation. The reason that you do that is because we allowed ANSYS to select the mesh size for us, and it has algorithms to do that, but as the human user, I am a little nervous letting the computer just fly the airplane for me without just checking to make sure that it did a good job. So a typical check on the appropriate mesh is to reduce the mesh size significantly, rerun the simulation for at least one example, and then check to make sure that the answer is consistent between the coarser mesh and the finer mesh. Now, of course, when you use a coarser mesh like the one that we've got now, the computational time is quite a bit lower. So once you verify that this works, you want to use as coarse a mesh as you can get away with for future simulations. But you do want to use a finer mesh at least once to validate that the coarse mesh does give you the correct result. So remember, we actually talked about this before. I pointed it out under mesh. I can go to sizing, and right now relative center is set to coarse. I'm going to click on this and I'm going to change it from coarse to medium to fine. And the moment that I do that, relevant center fine, ANSYS immediately responds by telling me that the old mesh that I've got on there now, the coarse mesh, is obsolete, right? It's pink, obsolete. And all of a sudden, that little check mark that was here before in the project tree has gone from a check mark to a lightning bolt, which tells me I need to rerun it. So everything else stays the same. The forces are the same, the geometry is the same, but the mesh needs to be rerun to make it more fine. So I'm going to right click and hit update. And what we will see here in a moment is a much finer mesh. See, those are much smaller rectangles or even perhaps squares. And now that I've got this, I'm going to rerun the simulation. So we're going to go to Solution, Solve. And again, this will take a little bit more time because the mesh is quite a bit finer. Okay, there we go. We're done. And I'm going to look at total deformation, and what I'm expecting is to achieve that same 3.126 times 10 to the minus fifth meter deformation that I had with the coarser mesh. And yes, in fact, I get 3.1263, so an additional significant digit, but the coarse mesh essentially gives me the same result as the fine mesh, and so I know that it is okay to use the coarse mesh moving forward for slightly more complex geometries, because I've done this validation of reducing the mesh size, rerunning, and making sure that the simulation gave me the correct solution. So there you have it. That is the entire lesson. Once again, this has been Dr. Matthew J. Traum from Engineer Inc. Thank you for your attention, and please check back in the future as we produce more engineering education videos. Thank you for your time. Take care. Hope to see you again soon. Bye.